Great. Okay. Yeah. So hi, everyone. I am Marylou Athanase. And yeah, I want to say thank you very much for giving me the opportunity to give this presentation live. I've got to say it's really nice to be able to be with you, at least virtually, directly from here in Bremen, Germany. It's more or less 11 p.m. here, but still I'm very happy to do this with you. I also want to give special thanks to all my co-authors here for this presentation. So that's the long list of names you should be seeing here under the title. And yeah, so I will now be giving you some updates on our latest progress on the use of nudging approaches for polar predictions, but in our AWI coupled prediction system. Okay, but what is spectral nudging? For those of you who were already there at Felix Bieten's presentation yesterday, you might already know a bit what nudging is. Some of you are probably even quite familiar with that. But for everyone else, I will still give a little reminder. So in free-running models, the weather is random and essentially determined by the initial state. And so in consequence, of course, we do not reproduce specific weather events. We do not reproduce the observed weather. And by a sense, the forecasting skill is quite limited by that random weather. And with spectral nudging now, the atmosphere model is no longer free, but instead it is nudged towards the observations, so towards a graded reanalysis, for example. And in other words, that means at each time steps, we add a nudging increment to push the model towards the observed state. So here you have the nudging increment formula, but you don't really need this. Instead, to illustrate what the nudging does, we have this little schematic from Helge Gößling. So imagine that at an initial state or at a time step t, we have an observed atmospheric pattern schematized with the gray background lines here. Well, in the free running simulation in red, we do not have the same weather pattern because of course the weather is random and it will continue being random in the next days. But when we start performing the nudging, schematized in blue lines there, so here we have the model with nudging, well, we will start being closer and closer to the observed state and remain close to the observed state for as long as the nudging is performed. So that is spectral nudging. And here our motivation were these two questions. So first, does imposing the winds in a climate model induce a better reproduction of the CS variability and of the CS variations? And if so, if we do manage to capture the CS variability better, how much does this improve the CS forecasts? So the simulations I will present here are based on the AWI-CM, so the AWI coupled climate model, but the latest version, AWI-CM-3. And AWI-CM-3 is composed of OpenIFS for the atmospheric component and FESM2 for the ocean. And here we nudge AWI-CM-3 towards the era 5 reanalysis, but we nudge essentially the large scale winds in a way that we leave the boundary layer and the smaller scale dynamics to evolve freely. All right, so what is the impact of spectral nudging on the simulated Arctic sea ice? So one first and rather unexpected consequence of the nudging on our simulations was the development of a cold Arctic bias. So on top here, you have the 2-meter air temperature in the simulations without nudging, the observations in the middle, and on the right with nudging. And all those are mean states. And at the bottom, you have the same thing for the CS concentration. And indeed, you can see that our nudged simulations are on average colder, that's the whole point, colder than the simulations without nudging. And we're still investigating the causes for this bias. So if you have key suggestions or ideas, feel free to drop us a message in the chat or an email directly. Yeah, we'll be very grateful. But in any case, despite this background bias, we still saw some significant improvements in the mean sea ice thickness and drift So here on top, you have the mean state for sea ice thickness, again, without and with nudging. And at the bottom, the same thing for the sea ice drift. And what we could see is that originally our free running simulations had too thick ice close to the Siberian shelf and too thin close to Greenland, which is kind of the opposite of reality. And with nudging, we have at least realistic Greenland to Siberia gradients, despite a tendency to overall too thick ice still. And this is likely because we start having more realistic ice drift patterns with a Beaufort gyre that was initially too large and now is a bit more realistic with nudging. We also checked that the nudging allows us to capture the variability indeed of Arctic sea ice. And we did this by plotting the correlations between the simulated and the observed sea ice concentration and sea ice thickness without nudging and with nudging for both parameters. And what we could see is that indeed, when we nudge, we have much higher correlations, especially along the continental margins compared to without nudging. So now, what are the consequences of this quite well captured variability on the sea ice forecasts? So in this section, I will be presenting results based on the AWI-CM-3 based prediction system. So here, our system assimilates sea ice and ocean data. And the little addition is that here, eventually, we also do wind nudging in the atmosphere in the OpenIFS. And in the following now, I will be presenting some test runs and figures that were provided by Svetlana Loza, who is also a colleague from AWI. And I want to thank her very much for that. Okay, so here is an example for a given day for a 24-hour ice drift forecast. And here on the left is the forecast without nudging, on the right with nudging, and in the middle, the corresponding observation on that day. And what we can see is that some patterns that would have been completely missed without the nudging can actually be captured when we have the nudging, at least on those shorter, relatively short timescales. So to confirm that the example I just showed is representative of any other day of the year, we plot the correlation of the 24-hour ice drift forecast, but to the observations and for the whole year, and for each U and V coordinates without nudging on the left side and with nudging on the right side. And what we can see is that without nudging, we had correlations basically oscillating around 0, and with nudging, quite high correlations above 0.7. And finally, we could see that when spectral nudging is performed, the data assimilation increments are reduced. Here you have this visible for the sea ice drift velocity without nudging on the left and with nudging on the right. And this reduction of the data assimilation increments, well, that is because the nudging is as expected. It isn't bringing the simulated state closer to the observed state. So that means that the data assimilation has to provide less effort at each assimilation time step. And we can also see this effect not only in the sea ice velocity, but also in the sea ice concentration and in the sea ice thickness fields. So, in short, we find that spectral nudging has quite some potential for the improvement of sea ice forecast initialization. We first checked that the spectral nudging, that spectrally nudging the winds in particular, led to quite a good reproduction of sea ice variation and variability overall. And we saw that the nudging was also reducing the data assimilation increments in our forecast system and also improved the 24-hour sea ice drift forecast. But since the sea ice drift is so strongly driven by the winds, it is quite expected that we had an improvement in the ice drift forecast. So a very important next step for us will be to see if and how the forecast for sea ice cover and thickness can be impacted by the nudging. Thank you for your attention. And yeah, if you have any questions, I can take maybe some now or in the chat.
Any kind of question on the audience? Yeah. François? Yeah, just here.
Hello, François Massonnet. I have a question about your cold bias or a suggestion maybe. Did you look at the integrated atmospheric heat transport towards the Arctic in the free-running simulation? I'm asking that because it could be that the free-running simulation has way too much heat going into the Arctic that somehow is compensated by some tuning that makes the ice look okay, but then when you constrain the width, you reduce the amount of heat going to the Arctic, and you create a cold bias. It is just the consequence of compensating errors in the free-running simulation. I don't know if I made myself clear.
No, that was perfectly clear. So indeed, we started looking into this, and we did not really find some major differences between the free-running simulations and the nudged simulations, which actually was quite surprising for us as well, because we also would have expected, yeah, something to at least stand out a little bit there. But yeah, maybe I just need to dig into this again. Thanks for your comment.
We have time for one more short question. We'll move on to our next speaker then and be right on schedule.